Hello everyone, and welcome to the first video in this series about how my binary to decimal converter works. In this video, I will introduce BCD and the double-dabble algorithm, and then show how the serial and parallel versions of a double-dabble device are related. This video is generally meant for Minecraft Redstone creators, but the topics in this video are generally applicable to all of computer science. First off, what is BCD? People generally count in decimal, with the digits 0 through 9. This is how everyone is taught to count from a very young age. But computers, of course, use the binary number system with the values 0 and 1. Most people will not be able to understand a binary number at first glance. So what do we do if we want to show a numerical value to the user of a device, such as the output of a calculator or their high score in a video game? We have to show them the decimal version of that number. So we need a way to store a decimal number in binary. This is where BCD comes in. BCD stands for binary coded decimal. It is a way to represent a decimal number in a binary format. The way BCD works is that we split the binary number into nibbles. A nibble is just 4 bits of binary. Each of these nibbles stores the binary representation of each of the digits in the decimal number. For example, the value 23 in binary would be 000101111. But in BCD, it would be 00100011. The first nibble has a value of 2, and the second nibble has a value of 3. These values can then be sent to whatever display you have and decoded to show their values in decimal format. This 7-segment display by MatBatWings takes inputs in BCD to display the number 23 on the screen. But how do we convert a binary number into BCD? When you or I look at a decimal number, we can easily convert it to BCD just by looking at each digit separately and converting it into a binary nibble, such as the 2 to 0010 and the 3 to 0011. But how can a computer figure out what the BCD values should be? Somehow, the computer needs to convert a binary number it has stored into a BCD number to display to the end user. So what would an algorithm for this conversion look like? How can we take a binary input and convert it to a BCD output? This was a common issue even back with the earliest computers, so of course a solution had to be created. This solution is known as the double-dabble algorithm, or it is also sometimes called the shift-add-3 algorithm. I'll show you why. The double-dabble algorithm works as follows. First, you set up a register like this, with your binary number on the right side and all zeros on the left. This is where your BCD number will end up at the end of the conversion. The double-dabble algorithm only has 2 steps, and you just repeat those steps until the BCD number is generated. The first step is to shift your number to the left. This is equivalent to the binary number being multiplied by 2, hence the word double in the name of the double-dabble algorithm. Since we've doubled the number, we now need to take the second step, to dabble with the number. The second step is to check each of the BCD nibbles to see if they're greater than 5, and if they are, add 3. In this case, all the BCD nibbles are still 0, so we do nothing. Moving on to the next step, we shift again. Then again, we check if the nibbles are greater than 5. This time, the ones place nibble is 1, but that's not greater than 5, so we do nothing, and shift again. Now, the ones place nibble is 2, but that's still less than 5, so we do nothing, and shift again. We check and see that the ones place is now 4, so we do nothing, and shift again. Since we started with an 8-bit number, we'll shift 8 times total. So far we've done 4 shifts, so there's just 4 more left. After we shift, we check the nibbles and see that the ones place nibble is finally greater than 5. It's at 9 now, so as the algorithm says, we're going to add 3 to it. 9 plus 3 is 12, so we'll change this nibble to 12, or 1100. Now we move on to the next step and shift again. After we shift, we check the nibbles. The ones nibble is greater than 5 again. This time it's 8, and 8 plus 3 is 11, so we'll change this nibble to 11. Now we shift again. The ones place is once again greater than 5, so we'll add 3. 7 plus 3 is 10, so we'll change this nibble to 10. We've shifted 7 times now, and just have 1 more bit left to shift. So just 1 more shift and we're done. And that's the output. The tens place nibble is 7, and the ones place nibble is 5. So that is the BCD representation of the number 75. Now we've gone over the algorithm once. Let's try it again with a larger number, say 175. So we'll initialize the register with all zeros, and then put our binary number on the right. 175 in binary is 10101111. So we shift and check. Nothing is over 5 yet, so we shift and check. You'll notice that on the second shift, there is no possible way to get a number above 5. Since we've only shifted in 2 bits, the highest value 2 bits can have is 3. This fact will be useful later, but for now, we'll shift again. Now the ones place is 5, so we'll add 3 to make it 8. Then shift again, and shift again, and again, and again. Now both the tens place and the ones place are over 5. The tens is at 8, and 8 plus 3 is 11. So we'll set that to 1011. The ones place is at 7, and 7 plus 3 is 10. So we'll set that to 1010. And now for the final shift, and we're done. And now it has a 1 in the hundreds place, a 7 in the tens place, and a 5 in the ones place. Now that we know how the algorithm works, we just have to make a machine that can follow those steps. This machine by NeoMaster does just that. If we put in 10101111 and press calculate, then it will shift each of these bits in one by one and check each nibble for a value over 5. At the end, it outputs the BCD here at the front. If you're interested in this device, then check out NeoMaster's channel, linked in the description. This device is sequential. A sequential device is any device where the output depends on the input and also any internal state or memory that the device has. For this device, a sequential approach is unnecessary, so we'll use a different type of device called combinational. A combinational device is any device where the output depends solely on the input, and it does not have any internal state or memory. Luckily, NeoMaster created a combinational binary to BCD device as well. With this device, if we put in 175 or 10101111 into the input, then at the output we get a 1, a 7, and a 5. And we didn't need to press a button to start the calculation and wait for each step. It just calculated the output straight from the input. This device also uses dabble, but it looks very different to the sequential version. So how do we go from the sequential version to this one? Let's take a look. I'll use the number 175 as an example again. This wall shows each step that we took when converting the number 175. The black layers represent the shifts, and the gray layers represent the check and add. At this first step, we shifted the number over. Then we checked the nibbles, and none of them were greater than 5, so we didn't add anything. So we shifted and checked and shifted and checked, and this time when we checked, the ones place was 5, so we added 3 to make it 8. Then we shifted and checked and shifted and checked and added until we got the output. You can see that this board has all the same steps that we took earlier, but instead of separating the steps between time, we separated them with physical space. That's the key to turning the sequential machine into a combinational machine. All of these steps have to exist at the same time. Now, let's shift over to this other wall. These two walls both have the same data, but the bits are just spaced apart differently. Each bit here has one block between its neighbors. This consistent spacing will be necessary to show the transformation from this into the final combinational design. The blue line down the center separates the input binary number from the output BCD number, and the light gray lines separate the nibbles of the BCD output. This wall is a little hard to understand without the clear lines separating everything, so let's add some arrows to show how each of the bits move. Now we can clearly see where each of the shifts are. Each row of diagonal lines is a bit shift. Now, you should notice that we only have 8 bits as our input, but we have 9 bits as our output. So where did that extra bit come from? If we trace the 9th bit back up, then we can find where it came from. It turns out it came from the third step, where we added 3 to 5. Remember back when I mentioned that after 2 shifts, the number cannot possibly be greater than 5, because the maximum value of 2 bits is 3. This is where that's important. As it turns out, we can only ever add new bits on every third shift, because the 2 shifts before that will have no possible way to be greater than 5. Let's take a step back. You'll notice that the arrows follow a diagonal line down to the left, but if we take a look back at the dabble device, you'll see that it doesn't follow this diagonal line. The bits flow in a straight line from the input to the output. But we know that we need to shift the bits at every step, so how does this work? Let's go look at one of the shifts on the board. This top row of bits has to be shifted left for the first step. But what if we straighten out the arrows? We'll keep the numbers the same, but shift the entire board to straighten out the lines. Now the board itself is diagonal, but in the opposite direction, and we didn't change any of the values. We just changed how we look at them. Now, instead of shifting the bits to the left, we shift our reference point to the right. This results in straight lines all the way down the board. Now that the board is reorganized, it's easy to see that we have some bits poking off the ends that don't do anything. They're just extra, so let's trim those extra zeros off both sides. Now this is what a combinational binary to BCD converter is like. These are the exact steps that it takes. The board is still a little messy though, so I'm going to do one more thing to help organize it. If we come back over to the device, you can see these orange sections. These are the conditional adders. They do the step of checking if the value is greater than 5, and adding 3 if it is. Our board does already have this logic step, but I'm going to highlight it to make it more clear. Remember, each of the gray lines is where we checked if the value was greater than 5, and if it was, then we added 3. So the first time we did that is here, so I'll cover this up with orange concrete to represent a conditional adder. You'll notice that this conditional adder's input and output are both the same. That's because its input is less than 5, so it does not add anything. The second conditional adder is here, and its input is also less than 5. The third adder is here, and this one has its condition met. Its input is greater than 5, so the output will be 5 plus 3, or 8. There is a gray row here, which does represent a conditional adder step, but the input here will only ever be 2 bits, which, as we know, can never be greater than 5. So that means we actually don't ever need to check this step. I'll go through now and add in the rest of the conditional adders. Now that I've added them all in, you can clearly see that we have 7 conditional adder steps, which lines up with the check and add steps that we took in the sequential device. But if we look back at the combinational device, you'll see that there are only 5 rows of conditional adders. If we go back and look at the board, you'll see that the first 2 conditional adders can only have 1 or 2 bits as their input, and as we know, 2 bits can never be greater than 5. That means that these 2 conditional adders are useless, and we can just remove them, and we can move our first step to here. Now the combinational device and this board are practically identical. I hope this has helped you to understand BCD and how to convert binary numbers into BCD. Don't forget to subscribe if you don't want to miss the next in this series, which will be about how to translate this algorithm into hex to take advantage of Redstone signal strengths. And thanks for watching.